The next thing today to talk about is likelihood functions. So before we talked about the probability of, the likelihood of specific parameterizations for when we got 4 heads in a row. We looked at the probability of heads being 0, being 1, being 0.5. So we could actually extend that to look at any possible value of the parameter p, which is the probability of heads. And so it can range from 0 to 1. We can see the likelihood of any one of those parameterizations. And we can see that it starts at 0. You can't get 4 heads in a row if the probability of heads is 0, up to 1, which is the only way. You're always going to get 4 heads if the probability of heads is 1. So this curve is called a likelihood function. And notice it's not a probability density function. It does not, the area underneath it is not equal to 1. It doesn't have to have any of those limits or anything like that. It's just the product of the probabilities of each of the possible outcomes. So if we look at, we looked at one particular case where we flipped 4 coins and got 4 heads. There are 4 other cases. We could flip it and get 3 heads and 1 tails. We could 2 heads and 2 tails, 1 head and 3 tails, or 0 heads and 4 tails. And we could look at the probability, and we could look at the likelihood functions for each of those piece of data. So here's the data when there are 0 heads and 4 tails. Here's that same curve we saw before where there's 4 heads and 0 tails. And we can see that the likelihood functions are differently shaped. And so each of these curves corresponds to a wide variety of likelihoods given the same data. So each of these curves represents a likelihood of a different model given that particular data. And oftentimes the values down here are what's more important, and so you can use log transformation to look at the likelihoods of each different model. And in this case, it actually doesn't make it that much easier, but the maximum likelihood occurs here at 0.25 when 1/4 of the outcomes are heads. Here it's at 0.5 when half the outcomes are heads. Here's at 0.75 when 3/4 of the outcomes are heads. It turns out that in each of these cases, the largest value of the function occurs where the parameter estimate is equal to the number of heads divided by the total. And if we do a similar sort of thing where we have different data, but this time, instead of having different proportions within the data, we have different sample sizes of the same proportions, you can see that the curve also changes, but this time what happens, and we're looking at the logs here, is that it goes from being flat, where lots of different possible models have similar likelihoods, to becoming more and more steeply curved, where the area with the best likelihood gets more and more narrow. In these cases, each of these collections of coins, 1/3 of them are heads. And you can see that this line, which occurs at 1/3, matches the highest point of all of them. So the parameter value of the maximum likelihood doesn't change with sample size, even if the likelihood itself does. So that's what the useful thing about likelihood functions are. And they give us this cool thing called a maximum likelihood estimator. So we can see that in many of these functions, the position of the parameter with the highest likelihood doesn't change with the sample size. So here's with 5 heads and 10 tails. This is not log scale, this is a linear scale. You can see that the maximum likelihood here occurs at 1/3. So that 1/3 is our maximum likelihood estimator. And we'll talk a little bit more of those in a second.